The sliding ladder. We have a 13-foot ladder. It's leaning against a house when its base starts to slide away. Okay, according to the suggested guidelines, let's get a picture going. Here's the side of the house. Here's our 13-foot ladder. It forms a right triangle with the ground and the side of the house. Okay, so we've got this 13-foot ladder and it's sliding away. At least its base is starting to slide away. So it's sliding in this direction right here. Okay, as the base is sliding to the right, think about what's happening with the top of the ladder. It's sliding down the wall. Okay, so the distance from the ground to the top of the ladder is decreasing, but the distance from the ground to the base of the ladder is increasing. All right, it tells us by the time the base is 12 feet from the house, so it's talking about, we're going to let this be X and this be Y. It's saying, consider that when X is 12 feet at that moment in time, okay, the base has a rate of change of 5 feet per second. So when X is 12, dx dt is 5 feet per second. All right, so let's look at our first question regarding this problem situation. How fast, well, that's a rate of change already, is the top of the ladder sliding down the wall at that moment? All right, so we need some symbols to represent a rate of change of the top of the ladder as it's sliding down. Okay, so we're supposed to be finding dy dt, a rate of change of y with respect to time. And if we think about it, as the top of the ladder is sliding down the side of the house, the rate of change, y is decreasing, which means the rate of change, dy dt, should be a negative number. All right, so we're finding dy dt, and we're going to find that when x is 12 feet, and dx dt is 5 feet per second. Okay, for this situation, we're talking about sides of a right triangle, so we're going to use the Pythagorean theorem to help us answer this question. So x squared plus y squared equals 13 squared. All right, so x is changing, y is changing throughout the context of the problem. 13 is not changing, the hypotenuse isn't, because that's the length of the ladder. All right, so once we establish the connection with all the ideas in the problem, we're going to want to differentiate with respect to time, apply the derivative operator to all terms. Derivative of x squared is 2x, but x and t don't match up, so it's going to be 2x times dx dt. Right, the derivative of y squared is going to be 2y times dy dt. And the derivative of this constant is just going to be 0. All right, your choices here are to either solve for dy dt, get it by itself, and then plug in numbers, or plug in numbers and then solve for dy dt. This problem doesn't look too difficult to isolate dy dt, so that's what I'm going to do for this one. Okay, so what I'm going to do is I'm going to move this whole term to the other side and then divide out 2y. So I'm leaving 2y dy dt. I'm going to divide both sides by 2y. Maybe simplify this, make the numbers easier to work with. Okay, now I'm going to plug in values. Right, x was what, 12? So we've got negative 12. Okay, y. Now I need y. Let's see, they didn't give me y, but I can find it by using the Pythagorean theorem. So when x is 12, I'll come over here and use the Pythagorean theorem to help me find y. This is 12 squared plus y squared equals 13 squared. So that's 144. 13 squared is 169. I'm going to subtract. Y squared equals 25. So I know y is either positive or negative 5, but in this context of this problem, y's got to be a positive distance. Distance is always positive. I know it's decreasing. The rate of change will be negative, and that'll take care of that. So we've got 5. Dx dt, I need to still multiply by dx dt, and that is 5. And pretty convenient that these two 5s will reduce into a 1, so my answer is going to be negative 12, and with the units feet per second. That makes sense. I should have had a negative number because the distance between the top of the ladder and the ground is decreasing, so the rate of change should be negative. All right, so another question that can be asked regarding this problem situation here is at what rate is the area of the triangle formed by the ladder, the wall, and the ground changing at that moment? So now we're looking at a different kind of situation here. We're looking at, okay, the rate of change of the area. Okay, so I'm not finding area, I'm finding a rate of change of area. So I'm finding dA dt. When all these conditions are met, when it says at that moment, we might have to use the values we found here previously. All right, so we're finding a rate of change of area. So we need the area formula for a triangle. All right, so it's a half base times height, but I'm going to use, instead of the b and the h, I'm going to use the x and the y. X and y are both changing, so kind of keep that in mind. Bring in your derivative operator. So dA dt equals, I'm going to leave the 1/2 outside of a bracket and just focus my attention on differentiating x and y. You could put the half with the x and let that be your first factor in the product rule. But I'm just going to leave the half outside. All right, so it's the first times the derivative of the second, dy dt, plus the second factor y times the derivative of the first, since neither x nor y match up to t. So let me plug in some values. All right, let's see, x was 12, dy dt was negative 12 because we found that in part A. Y we found in part A, what was y? Y was 5. And dx dt was given, and that was also 5. So this is negative 144 plus 25. I think that's negative 119. So it looks like the area is decreasing since I have a negative rate. So negative 119 over 2. Indicate units of measure. Well, we're talking about area, so we're talking about feet squared. Square feet over second. Area is two-dimensional, so we're going to use a feet squared. All right, so far with this problem situation, the ladder problem is pretty popular just because you can use a Pythagorean theorem. The shape that you're forming is a triangle, so you can use Pythagorean theorem. You can use it's a right triangle, area formulas, and then this last part right here. What's something else we can do with this problem situation? All right, it says at what rate is the angle between the ladder, here's the ladder, and the ground changing at that moment? So at what rate is theta, this angle changing? So the notation that represents what we're finding is a rate of change of theta, so d theta dt. Okay, at that moment again, maybe back to part A, we're going to be using that information. Okay, so first trying to find a rate of change of an angle here. We're not going to be using Pythagorean theorem. We're not going to be using the area formula. We're going to be using our right triangle trig ratios. So when I look at theta, and I have to find a rate of change of theta, I'm thinking sine, cosine, or tangent. I think the best thing to do is to avoid tangent, because if you were to use tangent, you're going to be doing opposite over adjacent, and opposite over adjacent gives you y over x, two unknowns. Okay, I'm going to take advantage of the hypotenuse that's constant. So I'm going to use sine, and I'm going to set up the trig ratio. Sine of theta equals y over 13. So if I'm finding d theta dt, I need something with theta in it, and that's going to be a trig ratio. Okay, y is changing, but 13's not. We have the equation that ties everything together. We're going to differentiate it. All right, the derivative of sine is cosine. Leave theta alone, times the derivative of theta with respect to time. So here we've introduced our d theta dt, which is precisely what we need. Okay, d theta dt. Okay, and let's find this derivative over here. Well, think of that as the constant multiplier 1/13. 1/13 times the rate of change of y with respect to time. All right, this parentheses is for cosine of theta. On this example, I'm going to plug numbers in first, and then I'm going to solve for d theta dt. Either way, I have 1/13 and dy dt. Well, dy dt was found in part A. That's going to be -12. Okay, what we need to find is the cosine at theta. All right, so let's come back over here to where theta is. The cosine is going to be adjacent over hypotenuse. Well, at that moment in time that they're referring to, x is 12. So the cosine of this theta at that moment is going to be adjacent 12 over 13. All right, let's isolate d theta dt by multiplying by the reciprocal. All right, multiply both sides of this equation by the reciprocal. And then let's clean it up. Oh, I can reach across here and cancel the 13s. I'm pretty sure this was a 12 down here. So I will reduce this to a -1. So it appears that my answer is going to be -1. And the units here were going to be radians, and the time units are seconds. Okay, so for the latter problem, what we just saw was 3 different problems that we could solve. We could solve a problem that involves the Pythagorean theorem. You can use an area equation, or you can use a trig ratio to solve for some different things on this latter problem.